Hello, Atomic folks. Thank you so much for joining. And today we will look into defining scenarios, or we can call it defining views. Okay, and this is something the higher level discussion we started in the last video. So if you haven't watched this video of the previous video, please watch that because I set the stage for the multi scenario situation. And today I will go into defining them, but I will also give you even a little bit more background on where we are, how we are setting up this full chip timing flow. For those folks who are joining the first time, I think this is my 10th or 11th video in full chip timing. And before that, there is a series on block level timing, and both these series or playlists, these are for members, and membership if you're in US is $2.99. All right. Okay, so this example that you are looking at, and I mentioned that in a real chip, we have different corners, different views, different scenarios. Okay, so let's take a look at this. So first of all, we can have different modes. We can have functional, we can have different versions of functional, right? Depending upon where you want to enable all of those functional interfaces or logic, all the logic together, or you want to keep disable some of those. Okay, the way you disable it, this is more of a timing disabling, right? Setting case analysis, setting false path, defining a clock, not defining a clock, stuff like that. Okay, making clock asynchronous. So you can play with those things by putting your entire logic in one particular mode and another one. Okay, so but I picked typically we have one functional. I mean, you don't want to have too many modes. Okay, you try to combine all the function in one. You try to have scan in one, sometime two, but I'm in this example keeping scan, shift, scan, maybe capture in one. I think scan shift because capture comes more in a functional side of things, but JTAG another one. And you can have some more debugging modes, but I'm considering these three. So a chip can be run in these three different modes. Okay, and again the explanation of modes, and I even gave an example. So if you have not watched the block level timing flow playlist, please pick a video there and you will get a good idea of what a mode is and how we can enable disable it. Then comes process. Okay, process is also something that I have gone in detail during the block level. Okay, this is where we're talking about inter die. Okay, when you can have dies at a very slow. The variation on this is a device process kind of I'm talking about. Okay, so devices manufacturing can bring a very different variations in their channel dimension, in the threshold levels, which means different doping levels, and different caps and all that. We did discuss all the process also in the block timing flow. So this is not on die, this is inter die. Okay, so I pick slow, fast, and typical. Okay, you can add more. Voltages, I pick high voltage, minimum voltage, and non-minimum voltage. Okay, some people only, or some projects you would select just the two, or some just one. So temperature, I selected 3. Okay, these are the ones we already discussed. I'm seeing right now in the low technology nodes a lot of RC interconnect corners and other. We used to have just one purely process wise. Okay, this is process, and then based on a different temperature, because different temperature can have different resistances, so we extract one for a high temperature and we do an extraction at a lower temperature, so we have main and max PEF. But nowadays the width of those metals, metal variations, vias and metals, interlayered dielectric variations, that those can produce even variation within each metal. Okay, so nowadays we have more RC corners. I think I just not trying to get into details of it, but remember this picture that you see a statistical model where you have high C, R is on x-axis, C on y-axis, and you can have a low R, low C, high R, high C, and then some of the crosstalk corners. So your typical is here, but you kind of have this plot. So you pick some of the corners on this one. Not you can pick more corners if you want, but because these variations are becoming very significant in our small technology node. Small, I mean really 5, 3, now 2. Okay, so you need to consider some of those. So I consider 4 of those. So now how many unique, because you need to combine different possibilities, right? You can have functional with a particular voltage, with a process with a particular voltage and a particular temperature and a particular RC. So if you combine them, remember we have 3 what was the modes and 3 process, 3 voltages, 3 temperatures, 4 RC corners. How many become 324 views or scenarios? Okay, I think Tempest uses views, and the prime time uses scenarios methodology. Okay, so a lot. That's the basic thing. This node we're talking about 2-3 views, and we're talking about hundreds of views. Okay, so question is now how to run those. So right now we are in the full chip setup flow side. So we haven't entered into analysis or reporting phase. So we are setting it up. And we know that atomic flow is not that complicated, right? So one way is you have these 324 views. Some of them you need to decide. Okay, one thing I missed saying that. Okay, you need to decide. Okay, which one you want to use for setup, which one you want to use for hold. Some of them you probably need to check setup and hold, which are critical one can bring those. But generally, I mean, if there is a setup, if your clocks are good, your hold is not going to be a problem. But I'm putting a lot of conditions here. But that's more of a project type level methodology. Where do you want to really make sure you want to check setup and hold? Do you want to pick initial run with all the views or corners, and then pick a smaller set which are the dominant one, and then gradually at the end near sign off you also pick all of them? That depends on your methodology. You're trying to optimize your run time to close your design, and at the same time ensure that you're not getting any risk. So based on those 2 things, you basically select for what you need to do for your project. But one thing is you pick one view, okay, and run through the flow. So a flow is what? We are reading libs for that particular view. And then we are reading netlist, that's common, reading UPF, that may or may not be common depending upon the voltages, right? And then SPEF also depends on which RC corner are we reading. And or even if you not have only 2 SPEFs, which are min and max corresponding to different temperatures, for different RC corners, you need to, you're not doing extraction separately, but you are setting some RC scaling factors or derate factors. Okay, so those things which I put some dots here, can represent some of the changes in each view. Okay, even your SCC can be different. Is a functional one, is a scan, can have a different one. So basically you rerun the entire flow for all 324. You understand that? And do I hit that? Okay. Then the other possibility is, which is again was or will be or is the topic of today, that we go into definition view file, is that we define all the views in one file, right? As opposed to making individual changes here. It's all the changes in one tickle file, and we read it into the flow. Right, and then what you do is you say, okay, I want a setup on these views, and I want to hold analysis on these views. Okay, You do this, and that way you don't have to create every time a separate tickle files for each of those 324. You define it once, put all your definitions into what in the Tempest what you call view definition file, and source that tickle file, and that's it. You have all 324 running on one machine. But keep in mind, these 324 are running on one machine. Now, if this is a small design and you have a decent sized machine, that is fine. But if you have 1 billion instance block or die or chip, you're running like a 324 billions of those net list. Even if it's one list, but the timing graph will be multiple, right? Right? The timing graph will be much, much bigger, so you won't be able to do that. So for the big massive design, that's in millions, I don't know, depends on the machine capability and all that. So what do? So you can do a couple of other options. Okay, one way is you still define your view definitions in one file, your sources, so your setup is common. And then on the shell, on the Unix shell, you have created a top level wrapper run FC timing. And inside, you give an option or arguments which define the view. You give in a view there, and based on the view, it sets the right thing. Let's say it's just one view, it maybe define setup and hold both for them or just one of those. And then on LSF, for Intel that would be net batch, but for others in LSF, it will fire that on different machines. They can run on one machine if machine is big and can keep two jobs there, but you define your memory requirement, your CPU requirements, and you throw them onto the farm. Okay, so in that case, your views are not, all the views are not running on one machine, but actually they are all running on a farm of machines. Okay, so again, this one and this one, they are still kind of a single mode, single corner. Now they have the difference that in this case, you have a combined view definition setup, which you didn't have in the other case. So this is still an optimum way, but still you have to take care of firing that each of those jobs on each of those machines, and you need to monitor them. Of course, you need to make sure that your jobs are getting machined, they are running fine, there are no issues and all that fine. Okay, and eventually if one of them is not running, that's fine. Only that one is not running, other one will at least run. For some people, this is still an attractive thing because they are kind of distributing themselves, but each one of them is pretty separate, independent. So even if there are some crashes, actually they have data from others. Another way is that you use the tools these days can do this thing for you. So tool can have a master one, and they can have workers, or you can call them clients. So you have the view definition file, and the tool has some special commands. So it just distribute views. Now keep in mind, the tool is not in this case distributing the design. Design is single, netlist is here, but the timing graph for each view is running on different machines. And then it will also pull back the reports. When this is done, report comes from here, report comes from here, then you can combine report there. All right, this is called a distributed multi-mode, multi-corner case. Right? Keep in mind, this is different than what, for example, in the case of Tempest, is the distributed SD. That is different because that's where you're partitioning the design into multiple version so that eventually you can run those smaller jobs. So these ones are still running pretty heavy, pretty big ones, and they need bigger machines in this case. All right. Some people don't like it because here, I think sometimes implications can have one of them is crashes. So what happens in the pulling up? I don't remember all the full flow, but I have seen so far this is more widely used scenario that I've seen in the industry. All right, I think I'm gonna stop here. We still didn't get time to get into the views definition, so yeah, I will do it this next time, and we will maybe look into further a little bit more into DMMMC or DSTA conceptually. All right. Okay, that's it for now. Thank you so much for watching. I'll see you in the next video. Thanks. Bye.